So for our problem today, a turbine processes 5,000 kilograms per hour of water vapor at a pressure of 4,000 kilopascals and 300 degrees Celsius. The vapor enters the turbine at a velocity of 60 meters per second and is discharged at 200 meters per second, 3 meters below the intake of the turbine. The power output of the turbine is 570 kilowatts, and its heat losses are estimated to be 135 kilojoules per minute. A small portion of the vapor discharged by the turbine is put through a valve, which discharges the vapor at atmospheric pressure. We are asked to calculate A, the temperature of the vapor at the discharge of the valve, B, the quality of the vapor at the discharge of the valve, if applicable, and we're asked to determine if it's possible to determine the thermodynamic state of the vapor at the discharge of the turbine with only the information available. So the first thing that we're going to do is we're going to draw our system, as I've done here, where this is our turbine, this is our input and our output. As you can see here, I've drawn the output channel, and this is going to be our valve. So let's label the things that we already know. We know that the pressure at the beginning is 4,000 kilopascals. The temperature is 300 degrees Celsius. The velocity is 60 meters per second. Right here, I've drawn the 3 meter difference. So this is going to be 3 meters. Okay, we know that the turbine processes 5,000 kilograms per hour. We know that the heat losses are 135 kilojoules per minute. We know that the work equals 570 kilowatts. We know that the velocity here as it's exiting the turbine is 200 meters per second. And we know that out here, this is the end of the valve. And we know that it said that it discharges at atmospheric pressure, which means that the pressure here is going to equal 101.325 kilopascals, which again is atmospheric. Okay, now to make our calculations a little easier, I'm going to label some of these numbers so that we can keep track of where we're talking about. So at the input of the turbine, we're going to call this the first part. Down here is going to be position 2. Right before the valve is going to be position 3. Right after the valve, we're going to call position 4. And now we have everything labeled. At this point, we're going to look at the valve. And since the problem doesn't say anything different, we're going to assume that the processes of the valve are adiabatic. So, this means that when we calculate, we should know this formula. Q, heat, minus the work, equals the change in enthalpy plus the change in potential energy plus the change in kinetic energy, and all of this times the mass. Okay, now let's think about this equation with our adiabatic valve. Okay, we know that because the problem didn't say anything, we can assume that no heat is lost with the processes of this valve. We also know that in the valve, there's no moving parts, so there won't be a change in work either. No work. We're going to leave delta H alone for a second and skip over to potential energy. Since there's no difference in height that we're told about this valve, we can assume that this also goes to 0. No change in height. With kinetic energy, there's no change in speed that they tell us as everything moves through the valve. So no change in speed. And we're going to ignore mass for the time because there is a mass flow through the turbine. So we're going to ignore that through this equation. So what do we have left? This goes to 0, this goes to 0, this goes to 0, and this goes to 0. Okay, so at this point we know that delta H equals 0. Okay, what does that tell us? This means that this valve is isoenthalpic, which means that the enthalpy does not change. Therefore, we know that the enthalpy at position 3, this position, equals the enthalpy at position 4, here. And because we're not told that any processes occur here, we also know that this equals the enthalpy at position 2. Okay. At this point, we're going to try to calculate the enthalpy at position 1, up here. Alright. So you should be familiar with this graph of temperature versus enthalpy with compressed liquids and superheated vapors. At this point, we are going to look in a table, this table, of saturated water and pressure. Okay, we know from our problem that this system occurs at 4,000 kilopascals. So we're going to look at 4,000 kilopascals on this table in the pressure column, and we see that this corresponds with the saturated temperature of 250.35 degrees Celsius. So when we go back here, we're going to say that this saturated point at the top of the curve equals 250 degrees, 0.35 degrees Celsius. Okay, but we know that our temperature at which this occurs is 300 degrees Celsius, which is going to be over here in the superheated vapors category. So this means that our process is a superheated vapor. Now that we know that we have a superheated vapor, we're going to look in a different table of superheated waters. So we notice that this table is in terms of megapascals and that our equation is in kilopascals. So we have to do a quick conversion that says that 4,000 kilopascals equals 4 megapascals. Okay, now in our table we're going to be looking for 4 megapascals. So here we see a table of 4 megapascals. And we're going to jump down to the temperature of 300 degrees since our process occurs at 300 degrees. In this column, since we're looking for the enthalpy at position 1, we're going to look in the enthalpy column at 300 to see that our enthalpy at 300 degrees is, this is H at position 1, equals 2,961.7 kilojoules per kilogram. Okay? So again, we just got that straight off this table as soon as we knew what we were looking for. Now that we know delta H1, we're going to go back to using this equation to calculate delta H2 down here. Okay, so the first thing that we need to do when we're going to jump back to this equation is we have to calculate the change in potential energy and the change in kinetic energy, since now we're looking with a change. Okay, so let's start with kinetic energy. So the change in kinetic energy equals 1/2 the final velocity squared minus the initial velocity squared. And this is just a really common equation. Okay, so when we plug in our numbers, we have 1/2 200 meters per second squared minus 60 meters per second squared. And I got these right off our diagram that we did earlier. Oop, there we go. All right, so when we plug that into a calculator, we see that this equals 18,200 meters squared per second squared. But of course, we don't want it in these units because nothing else in our equation is in these units. We want kilojoules per kilogram. So if you look in a common table of conversions like I have here, we can see that 1,000 meters squared per second squared equals 1 kilojoule per kilogram. So this means it's going to be our conversion factor. So 18.2 kilojoules per kilogram is our delta kinetic energy. Next, we're going to move to the change in potential energy. Again, a really common equation, potential energy equals mass times gravity times the change in height. So what we're going to see again is that because mass is a flow through the system, it's always going to be constant. So we're going to ignore it again in this equation. So we're going to plug in 9.81 meters per second squared times our change in height, which is a negative 3 meters, as we see up here. Okay, now when we plug that into our calculator, we see that this is negative 29.43 meters squared per second squared. And again, we're going to do that same conversion to convert this to 0.02943 kilojoules per kilogram, which is much better units for our equation. Okay, so now we're going to plug these two pieces of information, back into this equation. So we see that Q minus W, again, equals the mass times the change in enthalpy plus the change in potential energy plus the change in kinetic energy. Okay, so starting first with Q, which we know from up here is 135 kilojoules per minute. But again, we don't want minutes, we want seconds. So we're going to take 135 kilojoules and we're going to divide it by 60 because there's 60 seconds in 1 minute. So now our units are kilojoules per second. Okay, perfect. So one thing to remember though is because this heat is leaving our system, we need to make sure that this number down here is negative in our equation. Okay. So next, we're going to subtract off the work that we have. So the work that we see is, again, straight off the table, 570 kilowatts. 570 kilowatts. A quick little side note, that kilojoules per second is kilowatts. So we're all set there. Okay, so now as we go over here, we are going to include mass for the first time. So we see that 5,000 kilograms are processed per hour. But again, we don't want hours, we want this in seconds too. So we're going to divide this by 3,600, the number of seconds in 1 hour. Okay, so now we have kilograms per second, which again is perfect. Okay, so now this is going to be multiplied by delta H. Eventually we want to solve for delta H, so we're going to leave that just as delta H. Okay, so now we're going to add on our potential energy, which is this over here. So that's going to be a minus 0.02943 kilojoules per kilogram, plus our kinetic energy, 18.2 kilojoules per kilogram. Okay, awesome. So now we're just going to plug all this into our calculator to eventually see that delta H equals negative 430.191 kilojoules. Now, as we know, this is equal to H2 minus H1, the enthalpy at position 2 minus the enthalpy at position 1. Okay. So, we know the enthalpy at position 1 from when we calculated it back over here on this table. So we already know this value. So now we're just going to use these two to solve for H2. So we then know that negative 430.191 kilojoules equals H at 2 minus 2961.7 kilojoules, which is our enthalpy at position 1. We're going to see that the enthalpy at position 2 is equal to 2,531.51 kilojoules. Okay, perfect. So, now that we know that, which is our enthalpy here, we're going to look back at our table again. And when we're looking at this table of saturated water and pressure, we remember that our system is occurring at 1 atmosphere, which is 101.325 kilopascals. Okay, and then we're going to jump to the saturated temperature, which is right next door, 99.97 degrees Celsius. This is going to be the temperature at the discharge of our valve. So this is going to be our answer to part A of our problem. So the answer to part A, the temperature at the discharge of the valve is 99.97 degrees Celsius. And you might be asking, well, why didn't we just look at this to begin with? And it was because we didn't know all the variables that we needed, so we had to go through all these steps. And then eventually look at this table to see that the temperature at 1 atmosphere is 99.97 degrees Celsius. The temperature here at the discharge of our valve, and the answer to part A of our question. Now let's move on to part B. Part B says, calculate the quality of the vapor at the discharge of the valve, if applicable. Okay, so let's go back to this diagram with temperature versus enthalpy. And let's label a couple things while we're here. So we know that over here is the saturated liquids. And over here is the saturated vapors. And this area in the middle is a mixture. Okay, another thing that we know is this line right here is an isothermal line, which means that it occurs all at the same temperature. So, at this isothermal line, this point over here on the saturated liquids line contains 0% vapor. I'm calling vapor just this V. And then over here on the saturated vapors line, this point represents 100% vapor. Okay, awesome. So now we are going to look at our table. And this is the same table that we just used for our last question. And we're going to look at the same line, and we're just going to travel all the way across. And we're going to look in this enthalpy section here. And we're going to see that the saturated liquids, HF, at this point is 319.06. So I'm just going to label that real quick, 419.06. And this is in kilojoules per kilogram. And then over here with the saturated vapors, which is going to be our other side of the curve, we see that it's 2,675.6 kilojoules per kilogram. I'm going to label that one too. 2,675.6 kilojoules per kilogram. Okay, perfect. So now we need to know the equation for the quality of a vapor. So H of the mix, the enthalpy of the mix, is equal to HF, which is our saturated liquid enthalpy, plus X, this is going to be our quality, times HFG. And this H of FG is the evap enthalpy. Okay, so now that we know that, we want the H at position 2, and we're going to say that that's equal to HF plus X times HFG. Okay, perfect. So now, using numbers that we already know, we know, and we just calculated, that H2 is this number. So we're going to plug that in, 2531.51 kilojoules equals HF, which is this one right here, 419.06 kilojoules per kilogram, plus X, which is our quality, times H of Fg. And H of Fg you also have to get from this table, which is this middle value, VAP, H of Fg. Okay, so that one's 2256.5 kilojoules per kilogram. Okay, perfect. So now we're just going to solve for this X. And when we do that, we see that X is equal to 93.62%. And this is going to be the quality of our vapor, part B of the question. And now we have our answer for part B. The last part of our question turns out to be kind of easy. It says, is it possible to determine the thermodynamic state of the vapor at the discharge of the turbine with only this information available. So when we look back at our drawing of our turbine, they're talking about right here at position 2, right at the exit of the turbine. Is it possible to calculate the thermodynamic state? So one of the main rules for calculating or finding a thermodynamic state is that you have to have 2 thermodynamic variables. And in this case, we only have one thermodynamic variable that we calculated, which is the enthalpy here at position 2. So because we only have one thermodynamic variable that we have solved for, we cannot determine the thermodynamic state because we need 2 to be able to determine that. So for part C, we're going to say no, it is not possible to determine because we only know and we can only calculate one thermodynamic variable. And there we go. Now we've solved all 3 parts to this question. Thank you so much for watching.